So today we'll do the last thing that could be on the final, which is 3.9. We started that on Thursday, so today mostly we'll just do more examples. I will be ending a bit early because I'm giving a test in the next class. So if it's 10:10, maybe someone will remind me if I haven't stopped already. Because just in case I mess up like that in this class with the test where they can't easily get it and I have to email it out. All right, so let me start with the basic one again. You'll remind me how this works. So a large spring. I suppose I could do it in inches, but that's okay. Spring has a natural length of 4 feet. So a spring has a natural length of 4 feet. If it takes 6 pounds to compress it to 2 feet, then find the work to compress it from 3 to 1 foot. Oh, so looking forward, so the only thing that hasn't test is this, and then part of 3.7 and 3.8. So since our last class is next Monday, we could have quiz Thursday, but I think what I'm going to do instead, so there will not be a quiz, is I will put up a kind of a mock quiz, just of that material, just so you can check to see if you're okay with it. And as with the other mock quiz, you can either just take it to see if you're okay with it, and I'll put up answers later, or you can actually upload it to me and I'll grade it as if it was an actual quiz. All right, so here, first thing is we just have the little formula for this, which is what is the force due to a spring? Our one, well, we have two little force equations that you need to know from physics. This one, and then force is equal to mass times acceleration, which hopefully you know. So what is it here? Anyone remember? This is k times x. So we have the one example. It takes 6 pounds to compress it to 2 feet. And in some ways, this will not be the best example, but we'll get it in the integral. That means it's k times 2. Therefore, the force is 3x due to the spring. In the real world, if you compress it or stretch it too much, it gets a little weird, but for short distances, it is linear. And then in the background, we know that work is equal to force times distance. Therefore, for something like this, where the force is not a constant, we need to do an integral. And we do the force times the distance. Because remember, what we're going to do is we're going to see what happens, how much work we do over a short distance, which is going to become dx in the limit. So this is force. And this is distance. And obviously, we have to do it over the example. These aren't great examples either. So here, what are the limits? And actually, let me this to here. So as it was 1 to 3. Now it would be 1 to 2.5. So here I'll just give it as weight. So here, since it's pounds, it's already a force. So if it's kilograms, we'd have to multiply by gravity to make it into a force. So for this one, since it's kind of the setup problem, I'll just give it to you in pounds. And now here, the reason I want to change it, because if it was 3 to 1, it would become 1. But remember here, we're not looking at the position, we're looking by how much it compresses it. So at 3 feet, I've compressed it by 1 foot. So this 3 goes to 1. It's been compressed by 1 foot. Yeah, thank you. And then the 1.5 is I've compressed it by 2.5. So remember, that's why I didn't want to leave it as 3 to 1, because then it would have been a 3, which would have been a little confusing. So remember, you're not putting in the position, you're putting in how much it's been compressed by. So x here is compression distance, as Tucker says. So here's kind of the background one, which is work is equal to force times distance. And if force is not a constant, then you're going to have to make it into an integral. So any questions on this? We also had the bucket one from last week. Okay. So I do a second example, which is similar to the last one we did on Thursday, where we're going to do it in a different way, even though we could still do it the way we do it here, but it will lead into the last type of problem we're going to do. I should be able to get off, but so I'll mostly just do. All right, never mind. Start over. Sorry about that. And I think I'm going to do it this way. That way I don't have to write as much. So we have a box that is 3 feet by 4 feet and 6 feet tall. And has a density of, say, 70 pounds per cubic foot. I want to find how much work does it take to empty it from the top. And remember what we're going to do here is we're going to assume kind of the weird thing is the way we're going to empty it is we're going to take a pipe, we're going to bring it down from the top, start emptying at the top, and then move the pipe down as it empties, as opposed to kind of the more typical thing you do, which is just put the pipe to the bottom and empty it from the bottom. So we're emptying it from the top as we're moving down. And let me give a distance. So here we could do it like the last problem, which is find what is the total force of all the liquid, and then see what happens as subtracting it like we did with the bucket. But instead, what I'm going to do is look at a cross section and say that each of those little cross sections, I'm going to move a different distance. And go through the pieces here. So we know that equal to force times distance. So let me start off with the volume of the little slice here. Which is, of course, 12. And then force is the volume times the density. In this case, in pounds. And remember, the reason it's sort of volume is we're assuming that it has a thickness of delta x, a little thickness that we're then going to let go to dx in the integral. Right, so the A, it really is an area because we're just doing the 3 times the 4, the area of the cross section. But we're thinking of it as a volume because we're thinking that there's a delta x there. There's the thickness. And then the work, which I'll put at the end, is then the force times the distance. And in this case, the dx isn't the little place that we move it like we did in the last problem. It's instead the little thickness that makes the 12 into volume as opposed to just an area. And here, what are the limits for x? And this is where you have to remember that what we're doing is we're moving the pipe down from the top. So what would be the limits for the integral? In other words, it's not. All right, so in some ways you can see it looks like x is 0 to 5. That's where the liquid is. But since we're moving the pipe down at 0, so 0 feet from the top, there's no water or no liquid. So we don't hit the liquid until we're a foot down. So therefore our limit starts at 1. We could, and I'll do this in the next problem, we could let x not be the distance from the top, but the distance from the bottom, in which case it would be 0 to 5. But then we'd have to switch x, the distance. The distance would no longer be x because that's not how far I move it. So x is the distance from a generic line somewhere in the liquid from there to the top. So here is similar to one we did last Thursday. So any questions on this? So as I said, if you remember the bucket one, we could do this one in a similar way, which is get the total weight and then see what happens as we move it a little bit up, because as we move it a little bit up, we'll have less of it that we're moving, and then we could let the dx be how far we move it. But when we do the next problem, we don't want it that way. It'll be more difficult. So we want it this way. Okay, so let me do, oh, so what? So 1 to 6 is, so here's x again. Notice it is the distance from the top to the line. So just figure out what the limits are for x, ask if I'm measuring from the top, when do I first hit the liquid? Because there's no liquid at the very top because it's not, the box is not filled. So it's a foot down. And then I keep going until it's empty, and I empty it when I get to the very bottom of the box, which is 6 feet down from the top. As I said, I'll do another one in the next one where we actually look at it from both ways. So any other questions on this? We will come back to the 1 to 6 thing. So pretty much we're going to do more examples like this. We'll just make the shape different. So here we now have that's supposed to be a tank. Not sure how I got take out of that. That is shaped like a cone with a height of, and let's do meters now just to be different. Let's say 10 meters and a base radius of, say, 4 meters. If we have a liquid up to a height of, density, since I started writing it that way, 800 kilograms per cubic meter up to a height of 8 meters, then how much work to empty? So let me fill in everything. So here's our little triangle. So that top line inside the triangle is the height of the water. The middle one is just a generic slice somewhere in there that if I take out, I get, because it's a right circular cone. The height is 10. The base radius is 4. And then I put in my generic, let's let x be the height from the top of the cone to that generic line. And again, what we're going to do is empty it from the top. Okay, so let me start as we did the last one, which is we want to get the force. And so therefore we need the area of the cross section, which is of course pi r squared. And now you can see there are kind of two problems. One is that is changing, so it's not going to be as nice as the last one. The other one is that the distance we move it is going to be x, the distance from that line to the top of the cone, which means we have two variables, and we can't deal with two variables. Luckily, this is a triangle, and we have, underline the two, we have that triangle and then the full triangle. What type of triangles are they? So they're two triangles that have the same three angles, and those are similar triangles. And what do we know about similar triangles? We know that the ratio of lengths is the same. Right, so if I put r over x, the radius of the small triangle over the height of the small triangle, that's equal to the radius of the big triangle over the radius of the small triangle. So for similar triangles, ratios are constant. And I can do it in either way. I could also do r over 4 is equal to x over 10. Doesn't matter which way I do it, as long as I'm noticing that the ratios are similar. And in particular, that gives us that r is equal to 0.4 times x. And now I've gotten rid of one of the variables, so I can actually do it. So the area is equal to the pi times 0.4x squared. And the force is that, so 0.16 pi x squared times the density as in the last one. In this case, I also have to multiply by what? So eventually x, but I mean in terms of the force, right? Because the x will be the distance, so this is the force, so we're going to have to multiply by distance to make it work. But so that's here. So why is this, unlike the last problem, is the volume in some sense, right? So gravity, right? Because this is the other force equation you need to know, which is force is mass times acceleration. In the last problem, you have to remember that pounds is a force, so we don't have to do anything to it. Kilograms is a mass, so we have to multiply by gravity. And then like the last one, as Rebecca said, we have to now multiply by x, and you'll tell me the limits in a second. So it is this whole thing, which I'll be lazy and just leave as it is. So the 0.16 pi times 800 times 9.8 times x squared. That is all the force. And then multiply by the distance to make it into work. So now think of what we did in the last one. Again, let's get the limits here. So what are the limits for the integral? And again, remember that we're measuring from the top. Right. Because it's 2 meters down that we first hit the liquid, and we keep going until the bottom of the cone, so we get it all the way down to 10. I said I was going to do both ways in this one, but I think I'll wait until the next one, because in this way, this one, doesn't really make sense. The other possibility is, instead of calling x the distance from the top to that line, I could call x this distance, but here that's a little silly, which you'll see after we do the next problem. So any questions on this? This is now our typical thing. So here, notice that the density is in kilograms, whereas we want a force. So again, the annoying thing is that in US we use pounds, which is a force, whereas the rest of the world uses kilograms, which is a mass. So if you have a mass, you have to multiply by gravity to make it into a force, because force is equal to mass times acceleration. So this is G. Any other questions on this? So I do one more and add a little something, not too much. Similar in the sense that the side is a triangle. So sorry about my English. I'll draw the picture. So to make it different, I'm going to make it upside down. So we have an upside down square pyramid that is underground. And when I'm, so here's 15. This is 20. Here's my generic line. If I take this cut, I don't get a circle, I get a square. So if I make that W, this is W by W, and this is 10, oh, radius, not radius, width. Thank you. This is 10. Oh, and then this is 5. So here we kind of have two natural things we could let x be. And let's try it with both. So here are the two distances that matter. The top distance from ground level to the generic line is how far we're going to move it. And the bottom little one from the bottom of the pyramid to the generic line is the height of the little similar triangle. So both of those kind of make sense to be x. And either one's going to work. So let me start with letting this be x, and then in a minute you'll tell me what the other number is. And let's go through the pieces. So we have that area is, of course, w squared. And like the last one, we're going to move it in terms of x. So we need to get the relationship. So what's the relationship between w and x? W over X is equal to 10 over 20. And then what is the force? It is that 1/4 x squared multiplied by 62.4, and anything else? So is that the force, or would I have to put something else in? That's a 1/4. And that's it. So, little thing, 62.4 pounds per cubic foot is water. Not that it really matters, but the liquid in this case really is water. And now we have to fill in this other line. So here, what is that distance in this case? So if the distance from the bottom of the pyramid to that line is x, then what is the distance from that line to the ground level? Which will come up. Here. And now that's our force. What is our distance? So not x, because it is this distance. This is the distance we're moving it, right? Moving it from the generic line up to ground level. So if this is x, then 25 minus x here. And so the 25 minus x is the distance. In this case, what are the limits for the integral? So x is just measured from the bottom. Therefore, here is liquid from, and here we're kind of going backwards. Zero to 15. The reason it's kind of backwards is since we're going from the bottom, we first hit water when x is 15, and then we last hit water at x equals 0. So notice here we're measuring x as the distance from the bottom of the pyramid. So here's one possibility, and then let me do the other possibility and talk about why we get the difference. So in this one, so here's my variation. So same numbers. But now let me call x the distance I'm going to move it. And again, this other one is going to be 25 minus x. But now the similar triangles are same basic thing, except now it's not w and x, it's w and 25 minus x. Right, so we'll do that in a second. So let me do the two, because you'll see how they relate. So if I do it this way, and instead of a quarter, so his area will be this squared, instead of a quarter x squared, we'll get a quarter 25 minus x squared times a 62.4. And in this case, I've made it the distance nice, because now the distance is x. because I'm saying x is the distance from my line to the top. And in this case, now we're measuring x from the top. So we are moving the pipe down. The first place I hit water is 10 feet down, and I keep going until I get to the bottom of the pyramid. So this is also okay. So there are kind of two natural places I could let x be. I can measure from the bottom, and so if you look at the original one, x is where there is water. And you can see there is water from 0 up to 15. Officially, what we're doing is we're asking, well, we're moving the pipe down, and I ask, I'm moving the pipe down from the top, and I'm asking, when do I first hit water, except I went too far. Right there. So in one sense, you would say, oh, it's 10 feet down from the ground level, but that's not what I care about because I'm measuring x from the bottom. So it's 10 feet from ground level, which is 15 feet from the bottom of the pyramid, which is how I'm measuring it. So officially, this should be 15 at the bottom, and I keep going until I'm 25 feet down, but that is 0 feet measured from the top. So in some ways, to make this consistent, this should be not 0 to 15, but 15 to 0. In this second one, it makes a bit more sense because we are measuring from the ground level, and we ask, well, when do we first hit water, which is 10 feet down, and so therefore our bottom limit is 10, and then we keep going until we hit the bottom of the pyramid, which is 25 feet down. So either one is okay, which means if you understand one of those two, you can just always do it that way. And a little thing, which I think I said Thursday, might have been before that, is since there's always a positive work, which is as I'm emptying the water, I'm doing work on the water, but the water is also doing work on me in some sense. Because for every force, there's a back force, and so therefore, we can always think of it as both a positive and a negative work. So if I'm doing a positive work on the water, it's doing negative work on me. So I don't worry about the sign. So that's why I don't worry about that. This top integral should really be 15 to 0. Because all that does is switch the sign. So to make these two integrals equal, it should be 15 to 0 and 10 to 25. So any questions on this now? What I'm going to do next, which will be the last thing, is I'm going to do a similar thing, except get rid of all the stuff, and you're just going to tell me what are the limits for the integral and so on. So we're not going to worry about force and so on, just worrying about the distance, what we're going to put in. Something like that. So any questions on this? Okay. All right, so let me draw another one, and we'll do the short version without all the words. So let me make it again similar to the last one. Actually, I'm not sure why I'm just not doing it. Drawing this, I'm doing almost everything, so I might as well do the whole thing. So here we have the same type of picture. We have now a cone, which is 20 feet tall, has a base radius of 8 feet, has liquid up to a height of 5 feet, and in this case, let's call it a platform instead. We have a platform that is 7 feet. Make it obvious that is a 7 feet above the top of the cone, and I want to find how much work to pump it to the top, to that platform. And so like the last one, there are kind of two natural things we could let x be. One is, again, the height of the similar triangle, and the other is how far I move it, which is that distance. So here I have a generic slice. I want to know how far is it from the top of the cone, or how far is it from that generic line to the top of the platform. And so like the last one, we have that the the r over the x, sorry. If I'm doing this one, r over x is equal to, I said r over x and wrote something different, sorry about that. R over x is equal to 8 over 20. And again, this is pounds, so I have to multiply by gravity. Not sure why I reversed the order, but that's fine. So there's a force. So there are two things I have to fill in. One is the distance I move it, and then what are the limits for the integral. So here, first thing is, what is this distance? That's how far I move it. And what are the limits for the integral? So first, let's do it in terms of how far I've gone down, which I'm, again, moving the pipe down. So let me fill in, this is 15 feet, this top part. So as I move the pipe down, I first hit water when I am 22 feet down from the top of the platform. But what is x at that point? And you can kind of see it with the picture, which is what's the smallest value of x that hits the top of the liquid. go to the bottom. If instead if I let this be x, so x is the distance I move it, then what would be the distance from the top of the cone to my generic line? So I've just switched the two. Instead of being x and x plus 7, I'm going to make the outside one x plus 7. What's now the other one? So the height of this similar triangle is x minus 7. You can see I've just switched the two. And everything else is pretty similar, so I'll just go straight to this, which is now my x. In this first part, wherever I see x, I'm going to make it an x minus 7. So I'm going to get area is equal to pi times 0.4 times x minus 7, all quantity squared. And force then is equal to that times 50. So give me a second. So what I'm saying here is what I have, so go back to my original picture. I have a cone that is filled with the liquid, and I'm going to pump give me a second. I'm going to pump to a platform that is 7 feet above the top of the cone. So if I let x be the distance from the line to the top of the cone, then it's another 7 feet to the platform. On the other hand, if I say x is the distance from the platform I can't really write there. If that's x, if it's x distance from there to the top of the platform, then it's 7 feet less just to the top of the cone. So again, going with this one, if x is the distance from my generic line to the top of the cone, but I'm going to pump it to the platform, which is an additional 7 feet up, then the distance from the line to the platform will be x plus 7. The distance to the top of the cone plus the 7 feet up to the platform above it. And here we're just going the opposite way, which if I say the distance is from the line to the platform, then it's 7 feet less, because this is 7 feet, to just the top of the cone. The one thing that makes it nice is now my distance is just x. So I've made the distance nice. And what would be the limits for x now? So now x is, I am moving the pipe down, and the question is, when do I first hit water? And that is 22 feet down, and then 27. And you can see if you compare this integral to the one above it, so this one here, we really are plugging in the same numbers, right? If I put in 22, so I'm going from 22 to 27. Well, if I put in 15, I get 22. So I'm going from 22 to 27. And same thing here, I'm doing 15 squared to 20 squared. Here I put in 22 to 27, which is going from 15 to 22 squared. So it's really the same thing. So again, whichever one you like would be okay. We could be weird and let x be this distance, but that would be silly because that doesn't really help us with either of the two. We'd have to get the new one to get the height of the similar triangle, and we need another one to get the distance I move it to the top of the platform. So neither one is better. So could do that, but it'd be silly. So any questions on this? So as I said, I'm going to end early because giving tests in the next one, so make sure I'm ready if there are problems like I did for our class. So what you're going to do for Wednesday is you're going to look at the homework in 3.9. So we'll look at least one more like this, and then we'll go over the chapter 1 stuff, which isn't on the final, but is in Calc 3. So we want to at least go over it quickly so you have it in the background for when you do Calc 3. Also, again, we will not have a quiz on Thursday, but I will probably put something up on Blackboard just with this type of problem and problem from the second part of 3738, the plate type thing, because both of those could be on the final, but we haven't had them on a quiz yet. So just if you want to practice it. So any questions on this? Okay, so that's it. So the usual thing, if you don't have any questions, we're done and I'll see you Wednesday. If you do have questions, stick around. So I'm going to stop recording.